group of functions that have some cool utilities. So here's a curated list of functions. You might recognize some of them, and they cover a wide range of topics, including Swift UI, Swift Concurrency, file I/O, wall pointer access, and more. And you'll find they share some common patterns. For one, they have a common prefix with, and then it's followed by a noun. And also they have at least one closure parameter, which I omitted for the sake of readability. So I call these with functions. And their signature has a common shape of with resource, and then takes a body of a closure type that takes in the resource and returns some results. And you can also return the same type of return value as the closure that you take in, and Swift will be able to infer that return type for you. And how you implement and use this type of function is basically prepare some resource before cleaning it up, and then execute the closure that your caller is going to pass in. And how you use it is you call this function, open up the closure, and do whatever you want with the resource that's handed to you. And what's good is that this function makes accessing the resource lexically scoped. So when you enter the closure, you get a resource readily usable. And when you exit the closure, this resource is cleaned up automatically for you. And if you're out of the scope of this closure, then you cannot access the resource. Also, scoped means that whatever mutation or operation you do within the closure will not leak out, ideally, to the outside environment. And yeah, you get cleaned up safely, automatically, and deterministically. Next, let's look at some examples. So the simplest, one of the simplest examples that I can find is this with lock from synchronization, which is in Swift. And what it does is basically give you a mutex lock that is acquired log for you, and then release it when you're done using it. So you don't need to worry about manually acquiring and releasing the log yourself. And this is how you use this with log function. If you call this with log function and increment the number on 10 different threads, you will be guaranteed that you'll get value 10 and not have any database. And this is its implementation that you can find in the Swift repo on GitHub. There's a lot of bells and whistles, but basically it boils down to locking the mutex before unlocking the mutex, and then do the body that callers pass in. Next up, let's look at the file system I/O example. So these two APIs are from the Apple Swift and I/O library. You can also find it on GitHub, and it's a library framework that you can use to develop web applications like servers and clients. It's basically Java's native framework, but written in Swift. And this with file handle function will give you access to a file handle that is managed for you. So this function will open the file and close the file after you're done using it. So you don't need to worry about manually doing those two chores. And this is how you use it. You pass in the path of the file that you want to operate on, and you get a file handle in the closure. And after you've done your work inside the closure, you don't need to remember closing the file yourself. So this is a pseudocode that tries to explain what it does under the hood. It opens a file for the mode that you want it in. It can be reading, writing, or both. And then it defers closing that file, and then you can do the work. So this is the actual implementation you can find on GitHub. But for the sake of readability and time, I'm not going to get into it. Next up, let's pick up the pace and look at some more interesting examples. So the first one is with animation and with transaction in Swift UI. I think this is a very popular API that people working with Swift UI is going to interact with every day. And with animation, it's basically a wrapper around with transaction. It just creates this transaction for you and passing the animation you pass to with animation. And the resource we're doing here is transactions. Transactions basically specify how Swift UI should update views whenever some properties on it change. And by using this function, we can override the default transaction if you want to update some properties. So its benefit is that if you want to use a linear animation to animate the change of a scale property and another animation for color, those two animations won't interfere with each other, and they won't affect the animation used to transition other views and properties. And it behaves kind of like a task local value, which I'll get into in a bit. Next up, this is a pretty nice example from the 0.3 Swift dependencies library. It's a dependency injection library by the two brilliant guys from 0.3. If you're not familiar with the library, it's their take on dependency injection. And basically, their idea is that you want to treat dependencies as environment variables. So you don't need to worry about injecting them, the pipeline or the tree to inject them. Let's say if you're using the Needle framework, you need to worry about building the tree of components. And what's special here is that you're sharing the same collection of dependencies. They're using task local value. You can be sure, as we'll see in their implementation, by the way, is that if you want to override the dependency to inject a mob in Xcode preview or in your unit tests, you're essentially working with the same dependencies that you're working with in the production code. And the benefit of this with dependencies function is that it can confine the overrides to the scope of the closure of this function. So this is a simple example. Let's say if you're working with the date from Swift, which returns a new value each time you call it, indicating the current moment in time, which makes it a very tricky object to work with if you want to write unit tests, because ideally you want to pinpoint the return value that you call date from to a specific date moment in time, so that you can assert on instead of getting a new value later when you're executing the unit test. And if we look at its implementation, it's very verbose, by the way, but just want to point out that they're using underscore current as a task local value. So what is a task local value? My understanding is that it's like a stack of value. Whenever you access the value of a task local value, you're accessing top of stack. And you can use this with value function to temporarily override the value of this variable within the scope of the closure of this function. So here's a demo. Hopefully it's, I guess you can see it. Let's say you have a task local value count with the initial value of 1, 2, 3. On line 9 here, if you just print the value out, you'll get 1, 2, 3. And then if you override its value using this with value function to 4, 5, 6, you'll get a new value 4, 5, 6, but only within the scope of this exposure. And then you can even nest another with value call to get another value. But the good thing here is that whenever you exit the scope of a with value call, you'll get back the value of its enclosing scope of the caller of this function. So this is its implementation on GitHub, and it's very clean with the. Also has a similar shape of the signature that we just looked at. You push the value onto the stack, and then you defer popping it off the stack, and then you run the operation that your user passes. This also has an async variant of this with value function, by the way, but the implementation is very similar. Next, I want to talk about a concept called RAII, which is an acronym that stands for Resource Acquisition is Initialization. I think it's a pretty neat idea, prevalent in a lot of object-oriented languages like C++, Python, and also Rust. Although Rust itself is not exactly a OO language, but it also heavily relies on this idea. And if I'm to add the omitted second half of the sentence, there will be resource release is deinitialization. That's completing the whole management of the lifetime of a resource that you're managing. And the concept states that holding a resource is a class invariant and is tied to object lifetime. So class invariant is a jargon that basically means that as long as this object exists, the presence and validity of the resource is guaranteed. So let's say you have a file handle. In that closure will be guaranteed that the file handle is pointing to the file that you want to work with. And it's not pointing to garbage, memory, or, and by the time you're done working with it, the file is closed automatically for you. And it's implemented in different ways in different languages, which we'll get into next time. You can also simulate this pattern in Swift using the deinit function if you're dealing with class or actors in Swift. So in C++, basically, if you're, again, dealing with a file here, you open the file or create the file, do whatever preparation you need to do in the constructor. You close the file in the destructor prefix with the tilde symbol. And then you can do other interesting things in other public functions. And it's implemented a little bit differently in Rust because Rust heavily relies on the trait. Trait is like protocols in Swift or interfaces in Java. And Rust has this drop trait, which has a required function of drop. And basically you can do the cleanup work if you implement this trait for your type that's managing a resource. And when a variable of your type goes out of scope, this drop function will be automatically called, and the resource will be released. And in Python, it takes the shape of context managers and with statements. So basically, this context manager can be a class, can also be a function or decorator. But if you want it to be a class, you need to implement the $_enter and $exit functions. And you prepare the resource and return it in the $_enter and release it in the $_exit. And after you did those two things, you can use this context manager in the with statement. The with statement opens up a scope that your resource is valid in, and when you go out of scope, you revert back the indentation, then this resource will be released according to the implementation in the _exit function. So in Swift, you can do this with the dinit function. So basically, you just close the file handler in dinit, and yeah, same idea as C++ and other languages. But a question that raises from this is, what if you're working with non-plus type in Swift? Let's say you want to work with struct or enum or a protocol. Then you lose access to the dinit function because those type doesn't have a dinit function. And my answer is naturally, you can use the with functions that we just saw. And indeed, if we take a look at some of the implementations of those functions that we just looked at, they are in fact dealing with struct and protocols. So yeah, they need this. Next up, I want to talk about two examples that's very different from the examples that we just looked at before, because they are async functions and they have to do with concurrency. So the first one is with check continuation. So this function also has a variant of with check throwing continuation, with unsafe continuation, etc. But these group of functions basically serve as the bridge between GCD callback-based asynchronous code and async await structured Swift concurrency code. And the resource we're working with here is continuations or program state. Continuation basically lets you resume the execution of a function manually. So there's also the proposal if you want to take a closer look at the bottom, but the tags are kind of dry. Let's look at two concrete examples. On the left here is a GCD implementation of a function that downloads some data from a URL using URL session. On the right here is the async equivalent of this function. And what's different here is that by the time you hit line 49, task resume, on the left here, this function will return immediately. And will immediately start executing the lines under line 53. And GCD will call your completion when it's done downloading this data. But you're not waiting for it. On the right here, this function does not return immediately after line 50. Instead, it waits for the continuation to resume. So the end of execution in this closure is actually one of these three lines instead of the last line in the closure. So that's what continuation does. Next, let's take a look at with task group, also in Swift concurrency. So you use this function to spin up multiple child tasks concurrently. And the resource we're dealing here is task groups. And what it does is it suspends the current task that calls this with task group function till all the child tasks created in the closure has either completed or been canceled, and the body of the closure finishes executing. So this is an example to download a list of images from a list of URLs. And first you spin out a group of child tasks by iterating over the URLs and add them as child tasks. And the child task will start immediately. And then you use a for awaiting loop to loop over the group to wait for the results of the child test. The good thing here is that by using the for awaiting loop, you exhaust all the child tasks till all of them finish. And by the time you hit line 14, you can be guaranteed that all child tasks has indeed finished. And you also arrive at the end of your closure. And then you can resume and return from this closure. What if you don't want to return anything? Instead, you just want to spin up some child tasks and let them do their thing. Let's say you want to fan out some messages to a list of clients. So here you're just spinning up some child tasks and you're doing nothing afterwards. Here, this closure does not immediately return or resume after it hits line 28. Instead, the Swift runtime will implicitly wait till all child tasks finish and then return from this function. So by using this function, you're controlling the execution, the suspension and resumption of your task. And to summarize, there are three big ideas that, at least that I can think of, that you can use this with function style for. The first one is RAI style lifetime management. It's useful if you're dealing with mutex, I/O, like the file system we just looked at. It can also be a database connection. And you get controlled access to some resource that, if not using this function, require you to manually clean it up afterwards. The second one is prevent global mutation. We can see this idea in the example of task local, or if you want to create a logging or analytics system, and you want to have a base level of logging that you can share everywhere, but change the logging level in some confined scope. And if you're doing analytics, you can share a same base owner as a company. So if I work for Tinder, let's say the base analytics owner is the company. But right now, I want to change the owner to my team, a revenue team, if I want to attribute all the errors that's happening inside the modules owned by my team, then I can also use this with function. The last idea is you can make this with function async. And by doing this, you can have detailed control over how the program executes. It's seen in the example of continuation task group or and task cancellation handler. I think this last idea is kind of less accessible for our day-to-day application developers, because in order to implement this behavior, you need to really dig into the Swift runtime, which I may not know about. And yeah, that's the end of my presentation. So because some of the examples that I just talked about, like Swift UI, is closed source, I tried to ask ChatGPT how to guess it worked under the hood, and it gave me two different answers yesterday and today. So hopefully the general idea still deliver, and if there's any audience from Apple or from the Swift team that knows the in and out of how it actually works, please tell me. Thank you.
A really cool talk. I answered with a question regarding how, for example, with task group works, you demonstrated Swift UI, but you also mentioned C++ use cases. How would you structure interoperability? Let's say you're processing data using I/O, right? Documents, maybe some plain text, and you want it to process quickly, so you send it to C++ and you chunk the data. How would you move the data, and then it's executing these child tasks, and how would you think about that structure and to make sure that it all completes completes the thing?
Yeah, it's a good question. The short answer is I really don't know because I've never worked with language interoperability. I've heard the term foreign function interface, and that's basically what I know about these type of things. Well, I did watch the video by 23 about the Swift lights. So there's I think there's a Swift interface for you to call C functions of SQLite in Swift, and you need to work with all the anonymous raw pointers and yeah.
Okay, a follow-up question. You mentioned guaranteed execution with functions.
Yeah.
Can you just briefly go over that again? Like, how do you, as someone that's newly working with these, what do I look for to get that guaranteed execution? Is there a return value I look for in the log, or how's that work?
Yeah, that's a good question because I think it's up to the author of the functions that we're using. So really, they can do whatever you want. Ideally, they are open sourcing their work so that you can check them out yourself. But if they are just doing the safe thing, like just preparing the resource, I mean, a little more about this slide. You can also change the signature of it. You can add more parameters. You can throw an error, and again, you can make it async. So you can even spin up a task here and like wait for a little while before returning the result. You can go crazy.
Any more? Big round of applause. Thank you.